Whenever you're ready.
Yep. Okay. Hi everyone. We're gonna get started. We have Fangxin Hong, and she is a senior research scientist in the department.
Hi everybody. So I am a clinical biostatistician. So I focus on oncology trials. Today I'll give you some idea about new approaches, new directions in toxicity assessment and reporting in oncology clinical trials. Then we know cancer therapy could be toxic. We kill cancer cells while we might also kill normal cells, mess up immune systems, and alter microenvironment. So it's important to assess and reporting adverse event, which is just a fancy name for toxicity, in cancer clinical trials. Currently, we use the CTCAE. It's a common terminology criteria for adverse events to assess a list of AE terms that commonly encountered during cancer treatment, using 5 grades, grade 1 to grade 5, to assess severities. Of course, grade 0 means no such toxicity. CTCAE was designed to be assessed by provider, doctors. So also, you know the cancer therapies is given by cycles. You heard like 4 cycles, 6 cycles. Each cycle is 21 days, 28 days. And AE usually access at least once per cycle. So naturally, repeated measurement, which we know very well. So, but conventional toxicity analysis usually only focus on maximum grade through the whole treatment period and report only grade 3 or higher toxicity. I give you 2 examples from my own publications. You can see how the toxicity was reported, either in table format or in text format. But it's very simple, 1 point maximum grade. So naturally, we can see, as statisticians, this approach fails to capture toxicity that evolves over time. Also, ignore chronic low grade. And chronic low grade actually might occur at significant expense of patients' quality of life. Grade 2 diarrhea, low grade, means 2 or 3 diarrheas every day for 6 months. So you can imagine. Also now, now we have a newer therapy, like targeted therapy, immunotherapies. Unlike standard chemotherapies, we have a unique spectrum of AEs, and patients may remain on this treatment for a prolonged period of time, 1 year, 2 years. Also, many have late effect, late treatment, late toxicity. So we really want to know what the long-term tolerabilities. Lastly, because AE are chronic, many AE might occur at the same time. It's meaningless to talk about treatment burden if you only talk about one AE. You have to talk about collectively the overall AE burdens, resulting from multiple AEs. So how do we measure that? So the shortcoming of the conventional toxicity analysis has been recognized. There are several directions we're going in these areas. So one of the approaches we're taking is to incorporate the dimension of time and includes chronic low-grade events. We started to adopt this approach in some of our own ECOG equine trials, because I'm an ECOG statistician. Last year, I gave an oral presentation at ASH, which is the American Society of Hematology annual meeting. I present a longitudinal toxicity analysis on one of my trials. I use checkpoint inhibitor. You might have heard about it, PD-1, PD-L1 blockage therapy. So in that, this approach includes a collective of novel graphic and analytical approach, not new to us. For example, the mean grade over patient, across patient, and we plot mean grade over cycles. And this one, we can see how the toxicity evolved over time, over repeated treatment. This one is clearly cumulative. It gets worsened with repeated treatment. And that one is not cumulative. Further, we can quantify this AE burden over time using area under curve, the AUC analysis, and compare between arms. So this is give you an overall picture across all cycles. Lastly, we can apply our beloved survival analysis, time to event analysis, to toxicity data as well. See, on the left figure, we show the risk of developing grade 2 or higher diarrhea. We can show between 2 arms, then one arm has clearly high risk of developing first event of grade 2 or higher diarrhea. Another direction in AE analysis, as I said before, we want to tackle the problem to develop a metric that measures overall AE burdens resulting from multiple AEs. Example, potential AE measurements can use maximum grade across multiple AE types, mean grade, or weighted mean grade. Again, how to choose weight, big problem. And once we have the overall AE burdens, then we can also analyze them using traditional or the newer approaches to see how the overall AE burden differ between two groups. Lastly, this is another approach, a new approach, not in toxicity reporting, but in assessment. As I said to you before, CTCAE was designed to be assessed by providers, not by patient perspective. Here, it's patient-reported outcomes, because we want to have the patient tell us how much suffer they have about type cancer treatments. And this approach called patient-reported outcomes, PRO-CTCAE, has been implemented in a lot of our trials. It's a new direction. But the problem is how to analyze them and reporting them. That's going to be a pretty interesting new areas of research. Thanks.
Thank you. Sorry, did anyone have any questions?
Oh, yes. I'm used to the department line talks. You done. Go. Next one. Any questions? Because I don't know how many of you have experience working on analyze trials. Because we always talk about efficacy. Everybody cheers when you say, oh, the treatment difference. We don't talk about toxicity much because you sacrifice toxicity exchange for benefit. But imagine you have diarrhea 2 or 3 times for a year. Then what's the quality of life? So, this is really, it's considered low grade. We don't even report you. Not in my table. But, so, this is a new direction. The FDA and NCI now, focus more on the toxicity because cancer therapy achieved a lot. Now we want to talk about, okay, go back, let's talk about how to give you a decent life while you improve your treatment efficacy. So that's how it comes from. And we all emphasize patient-centered treatment development. So we want patients to tell us how much they suffer, not like we tell, based on the lab measurement.
I have one question. What do you think we are doing a decent job in communicating toxicities to patients? And does this work goes in that direction, or it remains only as a research tool?
That's a very good question. I think not only patient, also the providers, the oncologist itself. We so used to see maximum grade. So when they could probably see that in background care. But when we present the graphic to them, they didn't even realize, oh, those toxins actually accumulating. They were fascinated to see the new approach. I think before we talk with patients, we need to educate our oncologists first, to let them have a comprehensive view about toxicity. Then we come together and we start to better make consent form, educate our patient. Any more questions?
Great, thank you. Next we have Kwonsang Lee, who is a postdoc in the department.
Hi, I'm Kwonsang. I'm postdoc fellow. I'm working with Francesca. Today I'm going to talk about an interpretable approach to discover effect multiplication. So effect multiplication is present if the magnitude of the treatment effect varies the level of covariance. So let's think about the effect of exposure to air pollution on lung cancer. We hypothetically assume that the effect for men is higher than effect for women. Then the effect difference between men and women implies the effect multiplication. So discovering effect multiplication is important for 3 reasons. First, we knew that effect differs by sex, then we can use this information to increase the precision of effect estimation. Second, effect multiplication can help develop a causal hypothesis. If men are more vulnerable to air pollution, then some researchers may think that there are some factors like gene mutation that can affect men and cause lung cancer. So testing this kind of hypothesis can reveal the causal mechanism between exposure and outcome. And third, effect multiplication can have public policy implications. So if a subgroup is known to be vulnerable, then or more frequent or thorough screening tests for lung cancer can be suggested to this subgroup. So nowadays, we have lots of method development in estimating conditional average treatment effect. And these developments are based on using machine learning techniques like BART and random forest and gradient boosting. And these methods really, perform really well, but they are hard to interpret. So if we want to estimate the effect for a certain targeted subgroup, then these methods can provide a good estimate with great accuracy. However, this doesn't provide any practical guidance which subgroup we need to look at. So this method, the current method, are not that helpful in understanding causal mechanism and defining vulnerable subgroups. So ad hoc procedure can be considered to extract information from complex model output. However, making inference based on post-processed result is difficult. So what I like to propose is to do honest inference by using a sample splitting approach. A larger data set can be split into two smaller data sets. So discovery data set and inference data set. The discovery data set can be used for discovering effect modification structure, and inference data set can be used for making inference. Since the discovery data set will not be used for making inference, so we can use any ad hoc or exploratory is to develop a interpretable model that has a similar level of precision as currently developed method. One simple approach is to find the best tree from a collection of trees provided by random forest. Another simple interpretable structure is a set of decision rule. And once we have structure, then we can use the remaining inference data set to answer two questions. First, we can check whether there is really effect modification or not. So effect modification can be discovered due to unmeasured confounding bias. So we can do sensitivity analysis to see how robust our discovery is. The second, we can test the hypothesis whether discovered subgroups have really different treatment effect than the population average. And testing this hypothesis will identify vulnerable subgroups. If we are interested in estimation rather than hypothesis testing, we can estimate subgroup specific treatment effect. And I'd like to show you a glimpse of our work. So we developed a tree-based method to discover effect modification. So the tree is discovered from discovery data set. And then we found that only 3 subgroups have different treatment effect. We tested several local hypotheses. And for example, the 3 groups are 1, 5, 6. And for example, the people aged between 81 to 85 with low socioeconomic status has the largest effect, exposure effect. And please check our paper there and for more details. Thank you.
Does anyone have any questions?
I may have missed this in the actual talk, but what are the benefits of actually splitting the data set into 2? Why do you have to do that? Why can you not do both in the same data set?
So if we want to discover effect modification, and I think we should do inference about the effect modification itself. But if we are just using just whole data just for estimate the effect, then there is some misfinding in that sense, because we use data for estimation and we use data for discovery effect modification at the same time, so we need to adjust for that.
Did you also look at the variance then of the proposal, because you want to look for a single tree, right? So that it's easier repeatable than, for instance, in random forest. But random forest is a smaller method and should
mean the variance of the discovery?
Yeah.
Yeah, so that's our first paper. So in our second paper, we are looking at the variability of finding trees. So we actually using a set of decision rules rather than just one single tree to increase to account for the variability.
Thank you.
Thank you.
And next up we have Lorenzo Trippa. He's an associate professor in the department here and at DFCI.
Thanks so much. So I devote quite a bit of my time in terms of research on adaptive clinical trials. So I start from one example. This is the schema of a trial InSight, which is a trial for glioblastoma. That is a specific tumor type in brain. And I want to emphasize a few characteristics. First of all, for every enrolled patient, we have upfront, before randomization, information on several markers. We are using CDK, GFR, and PI3K status. And this is information that we combined in a Bayesian model together with two outcomes. These are overall survival and progression-free survival. That's the time between the enrollment of the patient till the tumor progress. And the key idea is monthly we update our Bayesian model, and we try to do our best in order to randomize patients and accelerate the evaluation of those arms that looks to perform best. So not only we have variations during time of the randomization probability toward those arms that are performing best, but we also use the markers and try to match each individual with those arms, that subgroup of individuals. So you have at the same time point as the differences across different biomarker subtypes in terms of randomization. So I want to make a link between two research directions that are very close to this project. First one is how do we translate inference from Bayesian modeling into randomization probabilities. That's not trivial. There are many classes of approaches. People in machine learning during the 5 years done a lot of progress. It's quite famous, the story of having computers playing chess or Go. And the underlying math is very similar to what we are using. In this paper we published in JASA, the main contribution has been to look at different existing approaches. On the top of that, we proposed our own algorithms which try to maximize specific metrics of information that tell us how much accurate are the estimates at the end of the study, basically. And the key thing is it really matters in terms of operating characteristic which type of algorithms we utilize. And there has to be a good correspondence between the primary goal of the studies and the way we approach the problem, the way we do adaptation. This is the second line of research. It's completely different. One is trying to be innovative in the way we study and we allocate resources to evaluate new treatment. This is more on validating the algorithms. We have a data set that include figures that we extracted, information for several hundred of papers published on clinical trial. We have as patient level data for about 10 clinical trials and electronic records, both from the Farber and from UCLA. And what we try is to use this information in order to say how efficient are different approaches in which people try to develop new drugs. The most interesting result here in glioblastoma is that a large portion of patients is allocated to single-arm trials that evaluate new drug versus a fixed threshold. And we did a little bit of meta-analysis, very simple one based on random effect models, computed type 1 error, and what we figure out is that if you target a 5% type 1 error, what you get is a 35% type 1 error. So it's not that surprising that there are many phase 3 trials that fail after positive results in phase 2 setting. This is another schema of validation. What we said next, well, doing single-arm trials and comparing to fixed threshold, not a good idea. Let's try to use external data. And here's the result. The key result is that we expected variations in performance of different methods from causal inference. It actually doesn't seems to really matter, but they help quite a bit in removing bias and reducing the type 1 error. I finish instead of the conclusion with an advertisement. We meet and discuss these topics every Friday at the Farber. So if anyone is interested in regulatory science and methods to design or evaluate clinical trial designs, just send us an email, and we are happy to share our work, and we have weekly presentations. Thank you so much.
Does anyone have any questions for Lorenzo?
Actually, I have. Lorenzo, for Bayesian design and PFS as the feedback loop, so I'm sure you have done maximum simulation to show the efficiency power again. So have you find in your simulation studies, and is there some scenarios that Bayesian does not better, or in other terms inferior to the traditional, the conventional randomization?
Yeah, there are several cases in which that can happen. So in in brain cancer, a famous story is Avastin. It is a drug in which there was a huge effect on PFS, which in some sense it was fake because it was an artifact of the way the imaging was monitoring the variation of the tumor mass. So if that happened, for example, well, we translate misleading information into wrong actions, right? So yes, the answer is if there is a conflict between the two primary outcomes that you use, the Bayesian model can be less efficient than ignoring the PFS part. But still, we think it's better to include it. Okay, thank you.
Okay, and lastly, we have Yaoyu Wang, and he is the director of the Quantitative Biomedical Research Center here at the school.
Hi everyone. My name is Yaoyu Wang, and I'm fairly new. Well, somewhat new here. We started late last year and tried to establish a service center it's called the Quantitative Biomedical Research Center. And so this is kind of the introduction for the center, and we are actually right next door on the other side of the wall. So basically, we were established earlier this year after the whole team actually moved from Dana-Farber Institute as a bioinformatics service centers over there. And we provide two types of services to the community as a whole. And one is data analysis, and data analysis where we perform customized project design, data analysis, and mining service for experimental biologists, most part. And then also cloud computing service where we help people integrate and provide analysis tools to cloud infrastructure. And that's a lot of things that's kind of too happy for a happy hour. So basically, I want to illustrate it more like a situation of how we fit into the whole biological schema. So in the simple world of quantitative biomedical research or biostatistics, you have your researcher and kind of sitting there thinking about your equations, and then you start integrating data from different sources, develop your Bayesian models, and then develop your deep learning models where you can apply to allow the public domain databases, and then publish your paper, and you are really happy because you love it. And once you are very well established and you're really good, you start to have collaborators, and you have your best pal on the other side of the aisle doing the research and then generating a lot of data that you can actually build your model on public domain data and then test it out and evaluate it with your collaborator. And once you are very good, you start to have a bunch of them, and that becomes a not so simple world of quantitative biomedical research where you have tons of collaborators try to collaborate with you, and every single one of you actually want to take their data and then ask you to fit their data assets into your model that you developed about 5-6 years ago. You no longer have any sort of interest whatsoever of running them again, and again, and again, and again, and again. And to make the matters worse, people actually start generating large amount of the sequence data using NGS, and then the next thing you realize that your queue within the FAS fair sharing queue is very, very low, that you cannot run anything that's of interest. So that's where we come in. We kind of sit in the middle and try to collect as many of them, collect a good subset of them that actually fits our expertise and have our ability to work with them, design the experiment with them, and while working with the quantitative biomedical researchers within the department that actually taking their novel method and making it into a development. That's a production methods where it can be standardized. So since, as I mentioned before, we have been around for a while, so we actually have been, by doing a customized research, we have been getting involved in different area of research with other people, the basic genomic research, technology development, and a lot of the biomarker and patient stratification. And but one thing that after we move over here, one thing we really concentrate on is actually developing our cloud computing infrastructures. And primarily, we have two flagship software, the cloud native analysis platforms that we call the Go Cloud and NAV platform, and the WebAV platform, which is not my concentration for today, but it's mostly a data visualization tools that we have been developing for last decades, or like the group had been developed for the last decades or so. And so what is this CNAP thing that we have been spending our time on after we got here is that we want to develop platforms where we can actually make a connection between the big brain of the biostatisticians and the experimental biologists. So what CNAP does is that it actually provides a web interface that allow you to control and integrate all of the packages that you develop and make it easy for you to put it into a platform and connect with the Chrome Mouse and the Google Cloud. So the Chrome Mouse is the scientific workflow engine that the world develops, allow you to scatter and gather a lot of the process such that you can actually design to be able to parallelize it. And you have this peg that actually controls all of the storage and the process. And by providing input, GUI, and the window and the Docker that contains the most fantastic applications, you're able to quickly design a user interface with all the backends and allow the experimentalist to take their FASTQ file stuck on the Dropbox and then send it over onto the cloud. So this is two of the use cases that we actually developed. One is the exome analysis, such that we can allow the experimentalists to take their 100 exomes, put it in a Dropbox, get their VCF files overnight, or allow people who generate RAC data with dozens and dozens of pairing and sequencing file and be able to process that and obtain a report within hours. So since we pretty much get the whole workflow together only recently, we're starting testing now on the more production scales. So we are looking for volunteers. We are looking for exhaustive biostatistical researchers deal with NGS data that they don't want to touch, experimental biologists that have a bunch of data that nobody wants to touch, and researchers who actually have their fantastic method that they want to publish, and they make it available to the community, but have problem dealing with the UI and then get it onto the cloud. So, thank you.
Does anyone have any questions?
Yeah,
So if you would like to use your services, how about what you need to do?
talk to me.
Okay.
I'm right next door, right next, like right the other side of the wall. So, all right, no questions. We are available. Thanks.
Thank you. And that's all for today. Bar is still open.